Carbon nucleophiles are kind of a tricky little beast because we're looking at a negatively charged species, and carbons typically are not negative because they're very low in electronegativity and they're pretty small. So both those characteristics make them very unlikely to hold a negative charge. However, we have seen methods to make carbon nucleophiles in the past. So if you can, see if you can come up with any right here and see if you can come up with any. To that end, hopefully you were able to target some kind of easy ones. We talked about enolates in this particular unit, so that should trigger some potential. So that enolate resonance stabilized does get you a negative carbon. So that would work because that could be a nucleophile. The other one, acetylides, where you take an acetylene with some kind of R group, that hydrogen has some acidity so that when spiked in the presence of a nice strong base like sodium amide, that base can come through, remove the hydrogen, and that would also get us that carbon nucleophile through an acid-base reaction. Another one that could potentially come up, or you may have thought of, and I'm sure there might be a few others, nitriles. The cyano group has a negative carbon. One of the things that you might notice within each of these three examples, though, is that they're all introducing some other functional group, okay? Be it a carbonyl, be it a triple bond. So we need to somehow modify the chemistry of the carbon to allow it to hold that charge. And that's what makes carbon nucleophiles tricky, is that you're now limited by that other functional group's presence. Okay? So for that reason, carbon nucleophiles tend to be well studied, and this is where we end up encountering a bunch of named reactions, and they're named because, well, it's not easy chemistry. So they all needed that extra thing to cause the carbon to be electronegative. So this is where we get Grignard reagents, okay, or even the organolithium reagents. And so these are special because we're going to start with an alkyl halide, so some kind of carbon-containing R group with a halogen attached to it. And then what we'll do is throw a metal at it, be it magnesium or lithium. Okay, lithium might stand out as a little bit more reactive and more susceptible to this, so you might recognize what's going on there. Lithium, when you throw it in water, big explosion, right? Okay, well, what's happening with the lithium when we throw it in water? Well, lithium metal has that extra electron. We throw it in with water, we get a radical reaction forming lithium hydride and hydroxide. Another lithium radical comes along, gives us lithium hydroxide, and that's getting us our neutral, or not neutral, but our stable state, our cation for the lithium. The lithium hydride can react with another water molecule to give us lithium hydroxide again and H2 gas. So the kind of violent reaction you're seeing is the H2 gas forming and then igniting because it's an exothermic reaction. So it's really lithium frantically trying to ditch that electron that's allowing this to occur. A similar system is going to happen with the magnesium. The special case with the magnesium is that it actually has 2 electrons, so it could really go through and do this process all at once. So at first it dumps 1 electron and 1 electron. The result is we form magnesium bromide, and then we still have 1 electron left over. We would have that R group with its 1 electron, because that sigma bond, there were 2 electrons there. If we're running it in a radical fashion, we have that extra electron that we have to account for. These electrons pair up, and then we'd end up with the R bond magnesium bromide. Because magnesium is lower in electronegativity than both the bromine and the carbon and the bromine pull the electrons away, effectively giving us R minus, Mg plus 2, and Br minus. Okay? It is that R minus that is our carbon nucleophile, and that's the big kind of kicker when we're looking at the Grignard reagent. So if you see something like this with our RMGBr, what you should immediately be interpreting that as is R minus, okay, or a negative carbon. The MGBr is part of this process, MGBr plus. It's usually floating around as a counter ion. This is a usually big mess of a molecule because it is a negative carbon. It is very reactive, and so it's great as a nucleophile. It's also great as a base. So we do have to be careful with the Grignard reagent and that it is exceptionally reactive, and it will pull hydrogens off of anything remotely acidic. The organolithiums, same deal. Okay, they've got that same reactivity. You're generating an ionic bond between carbon and a metal. So rare, useful, and tricky all at the same time. And because of that, that's why we name it for the scientist that discovered it, because he pioneered how this reaction works and what's the process behind it. In addition, if I say Grignard reaction, an advanced chemist, or not even that advanced chemist, will know that I'm talking about reacting a polar pi bond, like a carbonyl, with an organomagnesium compound. So a lot of information goes with just the name Grignard. Okay? And so that's why we tend to kind of push that you memorize that name. So rare carbon nucleophile. Okay? Why is it useful? A carbon nucleophile. We've got carbon electrophiles everywhere. If I now bring in a carbon nucleophile, I can bond two carbons next to each other. I'm now looking at actually building a larger structure. That's pretty phenomenally cool. Up to this point, all we've done is kind of cycled functional groups. Now we can build. Neat. Okay? And then tricky, well, it's the same reason why it was problematic as rare, is that it's exceptionally reactive. That negative carbon can react with electrophiles. It can also react with bases. So we could put in a nice little electrophile here of our carbonyl. So our R minus can do a great job attacking that carbonyl carbon and bust that open. It could also react with acids, say water. Okay, what would that produce? So if we ran through those reactions, the top one would give us our nucleophilic addition reaction, where we now have our carbon, our oxygen, and our R group. We'll address charges here in a second. And in the bottom one, we'd end up with RH and OH. OH minus as that charge comes out. In the top case with our nucleophilic addition, we'd have the negative oxygen. We would follow that reaction up with the addition of an acid to protonate that. And so we'd end up with now a larger alcohol, or we'd kind of revert our chemistry back to an alkane. So we have to be aware of both of those chemistries when we're going through and looking at reactions with Grignard reagents. And it is in fact incredibly common to see trick questions where there's both an electrophilic site and an acidic site within the same molecule. Grignards will preferentially act as bases, so be careful. Okay, so our mechanism, I actually already drew out. Not a big deal to know this. This would be known as our set mechanism. Set for single electron transfer. Okay, so we go through, we've formed our diradicals. These can go through and react, and we'd now form our Grignard reagent. Studies have gone into proving that this is indeed the mechanism, but again, not a big deal. The big deal for you is, wondering where my button is, using all of these. And before you go, oh my God, that's way too much, let's simplify this a little bit. Okay, let's just look at the top one for the moment. So that top one, we're taking a simple carbonyl with just two hydrogens on either end. So we're starting with formaldehyde. And what we're doing is reacting it with that nucleophilic carbon. Okay, the nucleophilic carbon attacks the carbonyl. We break open the pi bond. That gets us our negative oxygen and our happy new carbon-carbon bond. We then follow a step 2, right? Because remember, we don't want the acid present at the same time the Grignard is there, where we add H+, protonates, and ta-da, we now get our alcohol. What's cool about this is if we go through and look at this, we end with a primary alcohol. Okay? And as we saw in the last unit, our alcohols have lots of potential reactive sites. So not only did we expand the amount of carbons in our structure, but we've also kept a decent amount of chemistry behind this with keeping that alcohol functional group. If we push to the next one down on that list, okay, what is our difference? Well, now instead of being a formaldehyde with 2 hydrogens, we're now saying 1 hydrogen. So what we're looking at here is an aldehyde. The aldehyde, when it goes through that nucleophilic addition reaction, very similar in process. Note, all we're doing is really just changing that piece. Everything else is still the same, right? Continues across, and we still end with an alcohol. Except in this case, there's now 2 carbons connected to the carbon where our alcohol is, and we have a secondary alcohol. So really all these are attempting to do is show that it's just the same pattern getting repeated. All that's changing is kind of the back story on it, the surrounding area. And that surrounding area, in the case of the Grignard, really just changes what the output is. It doesn't change a whole lot about the chemistry. Right? Last one, instead of starting with an aldehyde, we start now with a ketone. And we can go through that same process. The ketone goes through, reacts, and we would get our tertiary alcohol. Okay, so all we're trying to show is that our Grignard can be used to make the varying states of alcohols. It just depends on what starting material you work with. This is where students can fall in the trap of saying, well, I'm going to memorize ketones and Grignards make tertiary alcohols. It's not that that's a false statement, but why did you bother to memorize that? Why not just bother to memorize the chemistry that's happening there? Because you can then apply that chemistry the same to each of these conditions without having to stress about the names of all those pieces. Okay? So I would argue you should sit on the chemistry. Your Grignard's a carbon nucleophile. It reacts with electrophilic carbonyls. Okay? That gives you enough freedom that you could now apply it out to a variety of other reactions, and that's going to put you in a better boat when it comes to an exams. Okay, so here we've got some practice questions. Again, I would like you to go ahead and pause and see what you can come up with for each of these. Yep, that's the space bar in front of you. I know it's staring at you. It's the biggest one on your keyboard. Try and hit that just once. You didn't hit it, did you? You thought you did, but hit it. Okay. Now what we'll do is go ahead and walk through these. So again, let's start with the top one. We look at our reagent CH3MgBr. We're talking about C negative. That negative needs to react with an electrophilic site. That electrophilic site needs to be positive, so it looks somewhere in the structure for a positive. We can kind of cheat here because our mechanisms are grouped. We're looking at it reacting at carbonyl carbons. There's our partial positive. Run the combination with them reacting with each other. I'm going to go through and use the abbreviation pH for our phenyl, which is a common abbreviation. O negative. Then we'd have our CH3. We follow this up with the addition of H3O plus in the second step. And we would now have our final alcohol, and we'd have our answer. Okay? Relatively straightforward. Since it does look a little bit staggered, we'll say this one's next. Okay, this one's going to add a little layer of difficulty to it, because in this case, you'll note that the Grignard reagent is on the left-hand side, whereas in most of our other cases, if we look, our Grignard is over the arrow. Okay? It doesn't matter where we place it. that organization largely comes down to an arbitrary placement based off of the size of the organic molecule. In this case, the Grignard here is the larger of these two molecules, and then we get CO2. Well, what is CO2? That's exactly the question, and why it gets asked is that students stumble and don't draw out the Lewis structure. Does that Lewis structure have a polar pi bond? It does indeed. So let's take those electrons, have them react. Let's break one pi bond at a time. There's the phenyl. There's the carbon of my CO2. There's that O. I didn't touch this one. There's a negative. And there we go. Okay. Now what happens is I add H2O. You'll notice I'm adding H2O and not H3O+. H3O+ is probably better, but I'm trying to be a little bit tricky here. H2O could then go through and protonate. It actually really should be H3O. And we would end with the carboxylic acid. So this is where you might go, but we didn't talk about forming carboxylic acids. Did the chemistry change? Focus on the chemistry. Okay. There is another carbonyl there. Could the Grignard attack a second time? No. Okay. The Grignard doesn't have the ability to pull off that second attack, and so it stalls out after one nucleophilic addition, and we end with a carboxylic acid. Kind of a cool reaction. Also very commonly done in lab. If we move to the third reaction here, what happens? Again, we have that negative CH3. We go, oh, we're just looking for electrophilic carbons. There we go. We run the reaction. We draw it out. And we'd say we have our answer, particularly because we have a multiple choice exam. We would select this as our answer, and then we would later find out that we were horribly wrong. And the reason we were horribly wrong, that is an OH. That OH started in the material. That is an acidic hydrogen. That acidic hydrogen will actually react with the CH3. And one of your potential multiple choice answers would be CH4. And you would be like, there's no way that would be the answer because it just doesn't fit any of the other patterns. That would be the answer because that's CH3 attacking the acidic hydrogen to form CH4. Okay? So that could be one of your answers. Another possibility for a valid answer for this one would be just redrawing the starting material. Okay? And you might ask, well, how did you get the starting material back? Well, the Grignard comes in, removes the hydrogen, then what's the second step do? It puts the hydrogen right back on. Okay? The last way this reaction could be shown for a possible answer would just be a straight up NR for no reaction. That's probably the least accurate because a reaction absolutely does happen here. It just doesn't do what we want it to do, which is that nucleophilic attack. Okay? So just be kind of aware of those limitations. As we continue to move through, we're now seeing an imine. Okay, which is a carbonyl with a nitrogen instead of an oxygen. Okay, how does this react? Oh, we didn't talk about that. Is it a polar pi bond? Yes. Okay, have your negative carbon, come in, run your attack. Of course, I changed my carbon change to run the other direction, which makes it a little bit more difficult to track where things are. My recommendation is maintain your geometries. You might ask, where did that second lone pair come from? Remember, the nitrogen started with a lone pair. We follow this up with the addition of H+, and we'd now have our final answer, just the tertiary amine. Okay, and depending on how nasty you wanted to get, you could make that worse. I won't, at least for this exam. So we could end with our amine. Cool. And then lastly, our Grignard could attack the nitrile. Booting this out. This is actually the dreaded question that I've been thinking was in here and couldn't remember if it was or not. And it turns out that yes, indeed it is. Okay. With our phenyl, With this as our weak alcohol or a weak acid, that will end up protonating it, and we'll end with the amine. Because that's a lie. This is the one that I keep forgetting on, and I will just have to try to fight to remember that I need to post an announcement about this one to fix this lecture, because I always forget how the Grignard reacts with that. Why? This carbon is still potentially electrophilic. However, that carbon up there preceding it is less electrophilic because that nitrogen can potentially resonate in. Okay, so we have to be a little bit careful with that. The nitrogen's nucleophilic characteristics or donating abilities are better than the oxygen, so that can limit sometimes that chemistry. So I'll have to look that one up to ensure that I lead you down the right path when we're reacting Grignards with nitriles. Okay, so after that, we've got some feasible and unfeasible Grignard reagents. So our textbook has done a pretty nice job kind of highlighting these. So if we look at the possible Grignard reagents, you can pretty much anything with a carbon that you could have had a halogen connected to, you can make a Grignard reagent. So lots of different possibilities for Grignard reagents. The ones down below end up not being good Grignard reagents. And you should be able to identify at least that first one as to why it's bad. This first one is bad because you have that acidic hydrogen, and that acidic hydrogen gets problematic. Okay, how about the other ones? Why do you think those other reagents would not work as Grignard reagents? As a hint, those little blue boxes are trying to tip you off to the chemistry associated with them. For that next one, you have an electrophilic site in that same place. If you have a single molecule with an electrophilic site and a nucleophilic site, what you've now generated is the monomer of a polymer. And that reaction would very likely polymerize, and that would just be a god-awful mess, unless that's really what you were trying to do. Okay, so not a good option in the formation of a Grignard. If we go through and look at the other ones, you'll note that little blue box. That blue box is denoting the positive characteristics that would react with the Grignard reagent. Okay, so what we end up seeing is a kind of internal reaction or an conflict. When you make a reagent, you want that reagent to do one thing somewhere else. Most reactions, we don't make a reagent so that it immediately reacts with itself, okay? Because that can be messy and problematic to sort out. So that's one of the things we need to be aware of when we're looking at our Grignard reagents, is watch out for those kind of hidden secondary chemistries that could get in the way. With that, I think we're done with the Grignard, but I'm going to hit next anyway just to see. Yep, and we'll move into the Wittig reaction in the next video. Okay, as soon as I can stop.